Hello all. In this video, we're going to illustrate the ideas of state spaces and state space search in the context of a number of different problems that are amenable to state space search. Some of them very practical in real world, and some of them are the kind of puzzles that people in AI have been studying for many, many years with state space search. We are also going to focus on one particular problem as our example, and we'll just keep coming back to that problem as a good way of imagining the positives and negatives of working with state spaces. I'm going to take a look at some examples of problems that can be solved with state space, just to sort of illustrate a variety of these, and we will look at more of those when we meet in class. So I've picked some that are more common and some that are less common. So examples of things that can be solved are thought of as state space search problems. One of those is this kind of a puzzle called a Sokoban puzzle. I have an example drawn right here. The general idea of these puzzles is they're sliding block puzzles. There's a world that you exist in. It's episodic because you solve this puzzle and then you move on to a whole new world. There's a goal location you want to reach, or maybe two, and you need to be able to move around in the space and push these blocks onto the goal locations. You can only push blocks from behind, and you can only push them if there's an open space on the other side. You can't push two blocks at once. So it's a nice, simple puzzle. It's actually a really great problem for doing state space search. And so we'll talk a little bit about this and use this as an example throughout my notes here. Other classic puzzles, sliding tile puzzles are a great example. You have the tiles, there's one missing, and you can slide the tiles up, down, left or right into that empty space, and you want to get some pattern on the tiles. It's a great example of the kind of problem that this was originally one of the problems they thought about with this problem, with this state space search. Robot navigation is another one. I mentioned that already. Here's one you might not think of. VLSI, very large scale integrated circuits. So these are often specialized circuits that are being designed for a special purpose. VLSI design, it turns out you can actually apply some of these methods to build up a solution to a problem that you want to solve with a chip, and then you can turn it into hardware. There are many, many, many others, and we will see some more in later examples. What I want to do is to take a little bit of a closer look at the Sokoban puzzle. So here we have our agent. It wants to push the red box over here onto the white square that has a heart on it, but it has these two blocks in the way that it needs to move out of the way. So this is a single state. It happens to be the initial state for this particular puzzle. We could define a set of states to be every possible placement of the agent of the two black boxes and the red box in the 9 squares of this puzzle room. And then we could think about what that means. How big would just all of the different possible configurations with this room, how big would that be? So this is a formula you can use to try to capture that. N times n factorial over b factorial times n minus b factorial. You can I did some of this math offline. There are basically actually more than 1,000 different configurations of this set of objects. So we're talking about this particular 9 square shape, the person, the two obstacle blocks, the goal block, and the goal itself. There are more than 1,000 different ways you could configure those. And actually with Sokoban puzzles, we actually have a much bigger grid, and you might include, say, walls that make this particular shape as a part of the state space as well. But generally, we would only think about one shape at a time. All right, the agent's actions here, they correspond to moving the agent up, down, left, or right. And the result of each action is a new state that maybe the agent has moved, maybe it hasn't, maybe nothing actually changes, and maybe other objects in the world move as well. So I have here a picture of the start of this state space, starting with our goal, and just sort of thinking through what would happen in each state if we did a particular action. So from the start, if we try to move the agent left, up, or down, it hits a wall and nothing changes. But if we move the agent to the right, it goes to the right, and the block that it's facing also is moved one square to the right. From here, we can't move to the right again because this obstacle block is up against the heart block, so we can't push the two of them together. We can't go down because there's wall there. We could go up. Up would cause the upper block to move up. Or we go left again, and that doesn't really progress the puzzle per se, but it is actually a legal move. So the state space then would branch out from here and cover all of the possible configurations you might have. Now, there are 1,000 configurations, I said. How many of them are actually viable? Many, many, many fewer than that. There are only certain ways that objects can move. And there are certain objects like the goal location that doesn't move at all. It's fixed in position. So what does that mean for us? Well, it means that building the full state space with all those 1,000 states is probably not that effective for us because much of that state space may never be reachable from this initial state. Instead, what we want to do is to build the state space from the initial state toward a goal state and only generate the states in the graph that we actually need. And that's going to lead us to the idea of search trees. I think I'm going to pause and I'll talk about search trees a little bit more in the next video. Next, we're going to take a look at search trees. So the search tree is a data structure. Actually, it's more of a conceptual data structure. We don't actually build the search trees in our algorithms either. But conceptually, we imagine a search tree as the portion of the state space that we are exploring while we are searching for a solution to our problem. So there are certain features of search trees. When we imagine them, the root of the search tree is always our initial state. Its direct children in the tree are the states that the various different actions could generate. So what other states could be generated from this parent state? And then we'll extend that. So the children each have their own children, which are the states you can reach by some other actions. So you put those two together and you've got two steps of the original agent. So the same continues all the way down the tree. Different problems may have trees that branch out dramatically. You could have a state that has 500 actions that the agent could take, and each of those leads to a new unique state. You could also have a very, very long, thin tree where there's really only one or two movements options for the agent to take at any given time. So all of our search algorithms are going to select one of the states or nodes in the tree, one of the leaves, and they will expand it to generate its children. Neighbors, if you think of it as a state space, but children in the context of the tree. And then we add those new states to the tree. So there are different ways of organizing the leaves on the tree, and fundamentally that's the difference between the different search algorithms that we're going to examine. At any moment in time, when we have this search tree that we're building, we have a set of the leaves, the states that we've generated, but where we haven't explored them and figured out their children yet. So those elements that are the leaves of the tree, those are the ones we choose from at each step to expand our tree, and we call those the frontier or the fringe set. Both terms get used interchangeably. All right, so as we do this search, the one thing that we really need to be careful about is making sure that we don't revisit a state that we've been to before. So each algorithm has to have some way of grappling with this problem so that it doesn't fall into a loop and end up just looking at the same sequence of moves and never making any forward progress. So generally, we're going to keep only the best path that reaches a particular state. And if we find another path that comes to that same state, we either won't consider it because we know that our current path is better, or we'll compare them and keep the one that's better. All right. What I've done in the diagram here is I've basically redrawn the diagram of the state space for the Sokoban puzzle, and I've drawn it as a state space tree. And what that means is I'm eliminating the edges that go from a state back to itself. Because if we have an action that doesn't change the state, we're not going to take those actions. We are trying to optimize our behavior, and that does not include doing steps that don't cause any forward progress. So from this initial state, the only move that actually generates a new state that's different is to go to the right. So that's going to be the first move in the tree. And from that point, we have two options. We can go left again, or we can go up again. And then you see it would continue to sort of spread out from there. That's our important search tree, using the Sokoban puzzle as an example. And you'll see many other examples with trees that, as I said, can be both narrow and sparse, or extremely thick with options. The more options you have, the more complex the search space is, and the more sophisticated the algorithm is. All right, there's one other topic I want to raise just so that you know what we're talking about, and that is we talked about how with any of these agent systems we have to be able to define what success looks like and how we're going to evaluate or compare different agents, different algorithms, different ways of solving the same problem. So I have a set of different features that we look at when we think about state space search problems. We can't always get an optimal solution on all of these. Often there's a trade-off, and we have to make a decision about how we want to solve the problem. So one criteria we can look at with our algorithms, we're thinking of our algorithms as being embedded in an agent, so our little agents, is completeness. And that means if we give it any possible problem of the type that it's supposed to work on, will it always find a solution if one exists? Is there a possibility that it might never find a solution? It's not complete if it can't always find a solution, or at least recognize in a finite time that no solution exists. Optimality, does it always find the optimal solution? Optimality and completeness are at play with each other. Optimality is also at play with time complexity and space complexity. How much time does the algorithm take to run? And this is where things get a little algorithmy. We actually might think about big O notation a little bit because it actually plays into these. Sometimes you have a problem that's complex enough that the state space search is too slow, and we have to do something to make that better. And what we typically do is give up on optimality. If we allow less approximate solutions rather than the most optimal, if we let ourselves be a little bit less optimal, we can often radically speed up the process. On the other hand, if we need the optimal solution, sometimes that means that we're going to pay the price in either time or space. All right, so this is the end of our overview of state space problems. We took a little bit of a focus here on the Sokoban puzzle. It's a great example because each puzzle has its own state space in some sense, and that means we have a really interesting situation where we wouldn't want to build a state space for every possible Sokoban puzzle. We really want to generate them on the fly and only generate the parts that we care about. In the next videos, we'll take a look at uninformed search algorithms, breadth first search and depth first search. I'll look at each of those separately, and we'll move on from there to some more sophisticated algorithms. In the meantime, I will see you very soon.